Hello, everyone. Welcome back. Again, this is Dr. MAMTamayao-Kieke. And today we're going to start our discussion on factorial designs. Okay, so suppose that an engineer is designing a battery for a device with the goal of making sure that the battery will withstand extreme variations in temperature. The engineer can, at the moment, select one design parameter, and this is material type. He or she has three options for this parameter, and the engineer recognizes that once in use, the battery will be exposed to temperature extremes, which cannot be controlled. However, for purposes of testing, temperature can be controlled. The engineer can then see how the different material types and temperature affect battery life. The engineer also wants to know if there is a material type that is robust across different temperatures, which means that the battery will have long life across the different temperatures. In this experiment, there is a need to investigate two factors simultaneously. Now, as you recall, in previous topics, the models we have dealt with so far deal with one factor at a time. For experiments like this battery design experiment, where we need to investigate two or more factors simultaneously, it is best to use factorial designs. Now, there are three advantages to using factorial designs. First, it results in efficient experimental design. Second, it allows for the detection and interpretation of interactions between factors. And third, it allows for more robust estimation of factor effects. Now, we will show this as we move along in this lecture, but let us first have some basic definitions and principles out of the way. A factorial design is one in which two or more factors are investigated simultaneously. In a factorial design, an experimenter varies the factors simultaneously. The experimenter is interested in determining the effect of each factor as well as how the effect of each factor change as the levels of other factors change. Now, let us familiarize ourselves with some terms. When we say effect of a factor, this is the change in response associated with the change in level of a factor. This could either be main effects or interaction effects. The main effect is the change in response related to the primary factors of interest, while the interaction effect is the change in response related to the interaction of factors, meaning how the effect of one factor changes as the levels of other factors change. Let's look at this graphical representation of a two-factor factorial experiment. We have factors A and B on the x and y axis respectively. Now, as you can see, there are two levels being investigated in this experiment, represented by low and high levels. The response y is shown in the corners. At low level of A and high level of B, the value of response y is 30 at low level of A and low level of B. The response is 20. At high level of A and high level of B, the response value is 52. And lastly, at high level of A and low level of B, the response is 40. Given the effects at different combinations of levels of factors A and B, we can compute for the main effects. Again, the main effects is the change in response related to the primary factors of interest. The main effect of A can be computed by getting the difference of the average effects at each level of A. That is, average at high level minus average at low level. This turns out to be 21. Based on this calculation, there is an average of 21 units increase in response when factor A is changed from low level to high level. In the same manner, we can compute for the main effect of B. Based on the calculations, we get an average of 11 units increase in response when factor B is changed from low level to high level. Additionally, we can compute for the interaction effects. Recall that interaction effects reflect how the effect of one factor changes as the levels of other factors change. To show this more clearly, let's look at a different example. Again, you can see at the corners the values of the response y. At low level of B, the effect of factor A is 30, whereas at high level of B, the change is negative 28. We can therefore say that the effect of factor A depends on the chosen level of factor B. With this, we can say that there is an interaction between A and B. Now, what is the magnitude of the interaction between factors A and B? We can compute this by getting the average difference of the effects for either factor. Using the numbers for factor A, we get the magnitude of the interaction by getting the average difference of negative 28 and 30. This turns out to be negative 29. You should get the same number if you get the average difference of the effects of factor B instead. Now, considering the magnitude of the main effects, the interaction effect in this example is significant. Interaction effects can be recognized graphically. The image on the left shows an example of an experiment without interaction, while the figure on the right shows one with interaction. As you can see, the response lines are approximately parallel on the left, while those on the right intersect. The intersection in the two-factor response graph indicates that interaction is present. Now, these graphs can be useful in interpreting presence of interactions, but should not be used as the sole basis for analysis because their interpretation can be subjective and their appearance can be misleading. Suppose that the factors are quantitative, or at least one of them is. A two-factor factorial can actually be represented using a regression model. You can see here the regression model representation of a two-factor factorial design. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 2 x1 times x2 plus eta, where y is equal to response and the betas are the model parameters related to effect estimates. The dependent variables, which are the x's, are coded variables that assume values negative 1 to positive 1. The model parameters are related to effect estimates. To compute for the parameters of the regression model, we can actually directly compute from the responses and main effects. The parameter beta naught is equal to the average of the responses, while the parameters beta 1 and beta 2 are 1/2 the main effects of the factors represented by x1 and x2. Beta 1, 2 is 1/2 the interaction effect. Now let's go back to this example. Recall that the main effects are as follows. You can see them on the slide below the graph. So the main effect of A, as you can see, the main effect of A is 21, that of B is 11, and the interaction effect is 1. To get beta naught, as we mentioned earlier, we get the average of the responses, and that would be the average of 30, 52, 20, and 40, and that is equal to 35.5. So you can see here, the beta naught is 35.5. Letting x1 represent the levels of factor A and x2 the levels of factor B, we get beta 1 by getting 1/2 of the effect of factor A, which is 21. Similarly, we get 1/2 of 11 for beta 2. And to get the interaction effect, we get 1/2 of 1. With this, our regression model for this experiment is as follows. Y hat is equal to 35.5 plus 10.5 x1 plus 5.5 x2 plus 0.5 x1 x2. Now, since 0.5 is small relative to the main effect coefficients, we can interpret it as the interaction effect to be not significant. Therefore, we can actually simplify the regression model to y hat is equal to 35.5 plus 10.5 x1 plus 5.5 x2. These relationships can be further represented through what are called as response surface and contour plots. The one on the left is the response surface for this equation, while on the right we can see the contour plot. The response surface is a three-dimensional representation of this two-factor factorial design with a plane showing the different values of y at different combinations of x1 and x2. On the other hand, the contour plot shows the lines for constant response y in the response plane. Now, since there is no interaction in the example we just discussed, the response surface is a plane, while the contour plots are parallel straight lines. Meanwhile, let's consider this model. Y hat is equal to 35.5 plus 10.5 x1 plus 5.5 x2 plus 8 x1 x2. As you can see, the value of the parameter corresponding to the interaction variable is high relative to the factor parameters. This signifies that the presence of an interaction. This is represented by the curvature of the underlying response curve and the curved constant response in the x1, x2 plane, as shown on the right. Remember that when the interaction is large, the main effects have little practical meaning. That means that the knowledge of the interaction effect may be more important actually than that of the main effects. Now this illustrates the relative efficiency of a factorial design to one factor at a time experiments. As you can see, as we increase the number of factors, the relative efficiency goes up. You can see this on the graph to the right. For example, at 2 factors, we need 4 observations for factorial experiments and 6 for 1 factor at a time experiments, and so on. So at 6 factors, you can see that the relative efficiency of factorial experiments is actually 3.5. As we have demonstrated, we can determine and interpret interactions in factorials. Moreover, with the efficient design, the estimated factor effects are just as precise as in one-factor experiments. Factorial experiments allow for the estimation of factor effects at several levels of the other factors. Therefore, it results in more robust estimation of factor effects. This means that results are valid over a range of experimental conditions. Now let's move on to two-factor factorial design. The simplest type of factorial design is one with 2 factors, or what we call the two-factor factorial. Say we have factors A and B that have small a and small b levels respectively. The experiment has n replicates, and each of these replicates contain all AB combinations. Okay, so let us go back to this example. Again, an engineer is designing a battery for a device with the goal of making sure that the battery will withstand extreme variations in temperature. And here you can see in this slide the observed life in hours of the batteries under each combination of material type and temperature. As shown, there are 4 replicates in this experiment. Note that the temperature levels were chosen by the engineer so as to capture the extremes that the battery is expected to be exposed to. Now, the factorial experiment can be expressed through several models, one of which is the fixed effects model. We start with the general case where y sub ijk is the specific response when factor A is at level I from where I is equal to 1 to A, meaning there are A levels for factor A, and factor B is at level J, where J is equal to 1 to B, meaning there are B levels. For the kth replicate, K equal to 1 to N, which means there are N replicates. And for this experiment design, all the ABN observations are taken, all of the ABN observations taken are selected randomly. This means that this experimental design is a completely randomized design. Now, a two-factor factorial with n replicates would generally be presented like this. At each of the AB combinations, as you can see, there are n replicates. Now, the factorial experiment can be expressed through several models, one of which is the effects model as expressed in the equation on this slide. Y sub ijk is equal to mu plus tau I plus beta j plus tau beta sub ij plus eta sub ijk. Now, both factors are assumed to be fixed, meaning the levels are predetermined from a limited set of available options. The treatment effects are defined as deviations from the overall mean. Y sub ijk is the specific response when factor A is at level I and factor B is at level J for the kth replicate. Mu is the overall mean effect. Tau sub I is the effect of factor A at level I. Beta sub J is the effect of factor B at level J. Beta sub ij is the effect of the interaction of A and B at levels I and J respectively. And epsilon sub ijk is the random error. Okay? The treatment effects are defined as deviations from the overall mean. Therefore, summation of tau sub I from I is equal to 1 to A is equal to 0. Summation of beta sub j from j is equal to 1 to b is also equal to 0. And summation of tau beta sub ij from I equals 1 to a as well as from j is equal to 1 to b is equal to 0. Okay, now we can also express the factorial design through the means model, which is shown here. Y sub ijk is equal to mu sub ij plus epsilon sub ijk for I is equal to 1 to A, J is equal to 1 to B, and K is equal to 1 to N. Mu sub ij is the mean at level I for factor A and level J for factor B. And this is equal to mu plus tau sub I plus beta sub J plus tau beta sub ij. And of course, as illustrated earlier, the regression model can also be used when at least one of the factors is quantitative. Okay, so what are the hypotheses that are tested in a two-factor factorial design? Now, we want to test the equality of the treatment effects. Okay, so in a two-factor factorial, the hypotheses are expressed as such for the factors, for the equality of the factors. Factor levels. So in a two-factor factorial design, the hypothesis for the equality of the treatment effects are expressed as such. H naught is such that tau I, tau 1 is equal to tau 2 to tau sub A, and these are all equal to 0. And the alternative hypothesis is that at least 1 tau sub I is not equal to 0. Okay? And then for the second factor, beta sub 1 is equal to beta sub 2 to beta sub b. They're all equal to 0. And the alternative hypothesis is that at least one of these is not equal to 0. Okay, now we are also interested in determining whether the treatments interact. These are the corresponding hypotheses for this. For H naught, tau beta sub ij is equal to 0 for all I and j. And the alternative hypothesis is that at least 1 tau beta sub ij is not equal to 0. Let's now move on to the discussion of the statistical analysis of the fixed effects model, in particular for the two-factor factorial for now. Okay, let us start with some notations, specifically for observation totals. Y sub I dot dot, okay, is the total of all observations for the ith level of factor A, or the road treatments. Okay, Y dot J dot is the total of all observations of the jth level of factor B, or the column treatments. Yij dot is the total of all observations at ith level of factor A and jth level of factor B, or the ijth cell. And then yi dot dot is just equal to the grand total, or the total of all observations. Okay, and this is how you compute for them basically. Okay, now the total corrected sum of squares can be written as such. You can see that the sum of squares is actually partitioned into the sum of squares due to factor A, sum of squares due to factor B, sum of squares due to interaction, and finally the sum of squares due to error. And this is actually the fundamental ANOVA equation. Note that from the last term, at least 2 replicates are needed for there to be an error sum of squares. And this can be written symbolically as shown. Total sum of squares is equal to the sum of squares for A plus sum of squares for B plus sum of squares of the interaction plus sum of squares for the error. And you can see here the degrees of freedom for each factor and the interaction as well as the error. And the total degrees of freedom is ABN minus 1. Now let's look at the expected mean squares. We know that mean square is equal to sum of square divided by degrees of freedom. So for factor A, for example, mean square A is equal to SSA divided by A minus 1, which is the degree of freedom for factor A. Therefore, expected value of MSA is equal to expected value of SSA over A minus 1. And this is equal to sigma squared plus Bn times the summation of tau sub I squared from I is equal to 1 to A over A minus 1. Okay, and so on. Now, if you observe these 4 equations, if it is true that there is no significant effect for factor A, for factor B, or even the interactions, then the second term for the first 3 equations would be equal to 0. Therefore, all expected mean squares would approximate the population variance, which is sigma squared. However, if the effect of any of these factors is significant, or the interaction is significant, then the mean square would be greater than, for the factor or the interaction, would be greater than sigma squared, which is also the error. Therefore, when we want to compare, or we want to know whether a factor, the effect of a factor or the interaction is significant, we get the ratio between MSA, or the mean square of that particular factor or the interaction, and the MS error. Now, going back to the notations that I showed you before, we can actually rewrite the ANOVA identity where total sum of square is equal to sum of square of A plus sum of square of B, sum of square of the interaction plus sum of square of the error. And we can write it by using the means, and these parameters can actually be computed using a spreadsheet. Of course, you can also compute for the sum of squares by using column, row, and cell totals as shown here. Okay, I'd like to point out that the sum of square for the interaction is equal to the sum of square for subtotals minus the sum of square of A minus the sum of square of B. And subtotals, the sum of square of the subtotals is equal to 1 over n times the summation double summation of y sub ij dot squared from I is equal to 1 to a and j is equal to 1 to b minus the grand total squared over abn. Okay, and we know the identity. Therefore, SSE is equal to sum of square total minus sum of square AB minus sum of square A minus sum of square B. Okay, and therefore we can also rewrite this as sum of square error is just equal to sum of square of the total minus the sum of square of the subtotals. And then we have the familiar ANOVA table. So it looks familiar to you, right? This is the ANOVA table for the two-factor factorial fixed effects model. On the first column, you can see the source of variation. Second column, you have the sum of squares. Degrees of freedom on the third column. And then you have the mean square on the fourth. And your parameter F naught on the last column. Okay. Again, your parameter F naught is just equal to the ratio of the mean square for the factor of interest divided by the mean square of the error. As we explained earlier, if this is large, okay, then it means that the factor effect is, or the interaction effect is significant. Okay, so here the sources of variation include your two factors or your treatments, A and B in this case. And then you have your interaction, your total error, and then your total. Okay, and then you have your corresponding sum of squares, your degrees of freedom, and then your mean square, which is just equal to the sum of square divided by the degree of freedom. Okay, now let's look again at the battery example. Okay, so what is 539 here? This is the sum of all the observations for the combination of material type 1 and 15 degrees Fahrenheit. Okay, so we basically get the sum of observations at different combinations of levels. So this is actually Yij dot. Okay, and then y dot j dot is just your what? Sum of all the observations under level J for temperature. Okay, so here you have 15, 70, and 125 as the levels for your temperature. For 15, the sum of all observations is 1738. For 70, 1291. And for 125, you have 770. And then yi dot dot is the sum of all observations under each level of material type. So 998 is the sum of all these observations here. So that's 12 observations and so on. Okay. And of course, y dot 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 is the grand total, the total of all the observations. Okay, given all those calculations, we can now compute for the sum of squares total. And this is just equal to this. Okay, so here we basically get the sum of the square of all observations minus the square of the grand total over ABN. Okay, and that value, okay, so if we go back to the table, that would be 130 squared plus 155 squared plus 74 squared, etc. minus the grand total, which is squared, which is 3799. Okay, we square that divided by 3 times 3 times 4. Okay, so that's 36. And if we compute that, we get SS total to be equal to 77,646.97. Computing for sum of square for the material, we just get the square of the totals for each level of material, okay, and divide that by B times N, okay, and subtract grand total squared over ABN. So in our example, that would be 1 over 3, 3 temperature levels times 4 replicates, okay? And then you have 3 totals because you have 3 levels for material type. Okay, so you have 998 squared plus 1300 squared plus 1501 squared. Okay. Minus grand total squared over ABN again. So SS material is equal to 10,683.72. And then for temperature, similarly, we get 1 over 3, 3 times 4 times these numbers here, okay, which are the totals of the observations for each level of temperature. So 1738 squared, 1291 squared, 770 squared. Minus, again, the same value that we've been using. Okay, so SS temperature is equal to 39,118.72. So the sum square of the interaction is can be obtained by using this equation. SS interaction equals 1 over n times the sum of the square of the totals, okay, totals of the observations under each combination of material type and temperature, minus the sum of square of the material minus the sum of square of the temperature. So our n is equal to 4, so 1 over 4 multiplied by, okay, so what are our cell totals? They would be this thing. So 539 squared, 623 squared, 576 squared, etc. Okay, minus, again, the same value. Okay, that's for the grand total over ABN. Minus the sum of square for the material, minus the sum of square for your temperature. Okay, and this would be equal to 9,613.78. Okay, now using your ANOVA identity, you can compute for your sum of square error, which is equal to sum of square total minus sum of square material minus sum of square temperature minus sum of square interaction. And we computed for all of those already, therefore we just need to calculate. And this would be equal to 18,230.75. Okay. And again, this is the ANOVA. Need to summarize all the numbers that we have computed so far. Okay, sources of variation, you have your material types, you have your temperature, and then you have your interaction, and of course your error. Okay, for sum of squares, we have computed for this, all right? And then degrees of freedom, we know that degree of freedom for material type is A minus 1, where A here in our example is 3. So 3 minus 1, 2. Same with temperature. We have 3 levels of temperature. So 3 minus 1, 2. For interaction, the degree of freedom is A minus 1 times B minus 1. So that would be 2 times 2, 4. For error, the degree of freedom is AB times N minus 1. So that would be 3 times 3, 9 times 3. That is 27. Okay, and for the total, that is ABN. So that's 3 times 3, 9 times 4, 36 minus 1, we have 35. Okay, as for the mean square, we just divide each sum of square by the degree of freedom to get these numbers here. So 10,683.72 divided by 2 is equal to 5,341.86, and so on. And for F naught, this is basically mean square for the source of variation divided by the mean square of error. So for material type, we divide 5,341.86 by 675.21 to get 7.91. And the corresponding p-value for this is 0.0020. For temperature, the p-value is less than 0.001, and for interaction, the p-value is 0.0186. Okay, now to determine whether material type, temperature, or the interaction is significant, we have to compare this with the test statistic for the particular factor and interaction given their degrees of freedom. Okay, so we have to compare the F naught here to F at the significance level, which for this problem is 5%, at degrees of freedom equal to the degree of freedom of the factor of interest and the error. So for example, for material type, we get F at 5% or 0.05, degrees of freedom 2 and 27. And the same is true for temperature, and that value is 3.35. Okay, and if we compare 7.91 and 28.97, obviously they are larger than 3.35, which leads us to the conclusion that material type and temperature are significant. Similarly, for interaction, F at 0.05 with degrees of freedom 4 and 27 is equal to 2.73, and compared to 20 or 3.56, okay, this is smaller, which means that interaction is also significant, and this is supported by the p-value, the very low p-values. Okay, therefore we can conclude that our data do not support the null hypothesis. So again, as they say, if your p is low, let it go. Okay, which means we let go of the null hypothesis that the effects for material type or temperature are equal to 0, or the interaction is equal to 0. And we conclude that there is enough evidence to reject the null hypothesis. This is a computer output for design expert. Now, if we plot the average life versus temperature for different material types, this is what we get. And as you can see, there is a decreasing trend. Okay, meaning the average life basically goes down as the temperature increases. Okay, however, for most of the temperatures, it seems that material type 3 has the highest average life. Although material type 2 has the highest material average life at 15 degrees Fahrenheit, it significantly drops as the temperature rises. Okay, and for material type 1, it drops significantly as soon as temperature hits 70 degrees Fahrenheit, okay, and stays low until 125. So it seems that material type 3 is the most robust among the different material types given this plot. Okay, now since we have concluded from our ANOVA that there seems to be a significant effect from the material type and the temperature as well as the interaction, we can perform multiple comparison using Tukey's test. Okay, so now before we perform Tukey's test, we have to take note that the interaction effect in this particular example is significant. Therefore, comparing effects at different levels of one factor, okay, might be obscured by the interaction effect. So to circumvent this problem, what we can do is fix the level of one factor and then compare the effects at different levels of the other factor. At this point, take a break and we will continue our discussion in the next video.